Hello, so in the previous two videos, we looked at partial fraction decompositions, two examples of partial fraction decompositions. So the first one here, this one here, where you've got the product of two linear factors on your denominator, and you can split them up into two fractions like this, with a constant on the top there and a constant on the top there. And similarly with this second one here, we looked at yesterday, ax plus b over cx plus d all squared. So this time again, you've got a constant number on the top over this linear factor there. And then your next fraction is going to be the square of this linear factor, and again, another constant number on the top. And we actually looked at a mixture of the two. So again, when you've actually got this linear factor here, this linear factor squared here, so actually altogether, you get a cubic of degree 3 on the bottom. If you have something up to degree 2, so again, a quadratic has degree 2, is a degree 2 polynomial, a cubic is a degree 3 polynomial, so on and so on. If you've got something like this, it could be quadratic, could be linear, could be just constant. You're always going to have this form here. So constant over the linear factor plus a constant over the second linear factor plus a constant over the second linear factor squared. So that's how, that's what we looked at before. Today, we're going to look at the last key partial fraction decomposition that you need to know. So it's going to be this one here. So let's say you've got a polynomial in x, so an expression in x up to degree 2. And let's say you've got a linear factor on the bottom and a quadratic factor on the bottom. So you can split them up into partial fractions like this. So a constant on the top over the linear factor, and then a linear term in x, so a linear polynomial over a quadratic, the quadratic term there. So yeah, this one's a little bit different because actually we've got to remember to have this linear term on the top of our on the fraction. And a key thing again that we need to remember is that for partial fractions to work, we need the degree of the numerator to be less than the degree of the denominator. So the numerator here could be degree 2, could be degree 1, could be degree 0, which would just be a constant term on its own. And the degree of the denominator in our case here is 3, because this is a cubic. When we expand the brackets on the bottom, you get a cubic, which is degree 3, because the highest power of x is 3. That's what the degree means. Okay, so let's look at like an example of how we could do this. So let's try and split this fraction into partial fractions. So this is going to be the same as a constant over 1 minus x plus a linear term, so bx plus capital C over a quadratic, this quadratic term on the bottom here. Okay, now let's multiply both sides by the denominator. So multiply by denominator of the left-hand side. So of left-hand side on both sides. And if we do that, we will get, so 3x minus 1 is exactly the same as, so this fraction multiplied by this denominator there. So the 1 minus x will actually just cancel out. So you're going to be left with a times by x squared plus x plus 7. Because again, when you do this divided by that, that cancels out with that. So that's why that works. And then plus, so now plus this linear term, capital BX plus capital C, times by, again, this denominator divided by this factor here. That's just going to be 1 minus x. Okay, so we get that. So therefore, so 3 minus x is exactly identical to, let's just expand the brackets here. So we've got ax squared plus ax plus 7 lots of a. And then expanding these brackets here, I'm just going to put these in square brackets. So you get bx, take away bx squared, plus c, take away cx. Okay, so that's our expansion there. And then this is the same as, okay, so you've got ax squared there, subtract bx squared there. Okay, so this is going to give us a subtract b lots of x squared. Now we've got ax there, we've got bx there, and a negative cx there. So actually, if we collect all those like terms, we get a plus b take away c lots of x. So that's the x dealt with. And then this constant term 7a, this constant term c there, 7a plus c at the end, as our constant number there, 7a plus c. Okay, so now we can match the coefficients like we did in the previous videos. So match coefficients. Let me write that again. Match coefficients. Okay, so now if we look at our left-hand side, we've actually got a 0x squared that have because we've got no lots of x squared on the left-hand side, but we've got a minus b lots of x squared on our right side. So equation number 1 is going to be 0 equals a minus b, because let's just underline this, a minus b must be equal to 0 there. Now how about our next equation? So 3 lots of x on the left side, a plus b minus c lots of x there. So our second equation, number 2, is going to be 3 is equal to a plus b subtract c. And then equation number 3, our very final one, that's going to be -1. So our constant number at the end there, -1, is equal to this constant over there. So 7a plus c. Let's try and make the writing smaller so we can have more space. Let's try that again. There we go. Okay, so now then, using equation number 1, we can actually say with certainty from number 1 here that a must be equal to b, because a take away b is 0, so a must be equal to b. Okay, so we know that. So now we can go to equation number 2, and we can say, okay, well, we've got 3 is equal to a plus b, but b is just the same as a anyway. So that's a and then minus c. So you've got 3 equals 2a minus c. So therefore, you've got that c must be equal to 2a plus 3, just by rearranging that. Okay, so now then we can plug this into our final equation down here, this number 3. So we can say that -1 is equal to 7a plus c, but we know that c is this 2a plus 3 that we just calculated. So we get -1 equals 9 lots of a plus 3. We can then take away from both sides, we can subtract the, sorry, let me just move my writing like this. We can subtract the 3 from both sides. We get -4 equals 9a, and that's going to give us a is equal to -4/9. Now we know that a equals b because we got that result there. So b is exactly the same. So b must also be -4/9. And c, well, we worked out c to be 2 lots of a plus 3. So c is going to be 2 lots of -4/9 in addition to 3. This is -8/9 plus 3. 3 is just the same as 27/9. And so as a final result here, 27 take away 8, that would be the number 19. So 19/9, and that would be our c value down there. Okay, so then our final partial fraction then, or our partial fractions, if we just again try and keep this on the same page. So our final result is that 3x minus 1 over 1 minus x times by x squared plus x plus 7 is going to be equal to, so a over 1 minus x, so -4 over, well, -4/9 over 1 minus x, like that. So that's our first bit there. And then our next factor, plus b, which is -4/9 lots of x, plus c, so plus this 19/9, divided by this x squared plus x squared plus x plus 7 there. And in fact, we could tidy this up a little bit if we wanted to. So we get -4/9 times 1 minus x for the first bit. And then the second bit, we actually just bring this 9 there and there to the bottom of the fraction. So you can write it like this instead. So plus -4x plus 19 divided by 9 lots of x squared plus x plus 7. And that would be our final result down there for the partial fractions. Okay, so that's just an example of how we can use this rule number 3. In fact, we can actually combine all 3 together. I mean, you're not going to get a question like this in the exam. You're not going to get anything more than 3 factors. I mean, here we've got 4 factors technically on the bottom of our denominator. You won't get more than 3 factors in your exams because the maximum number of factors that will be assessed in A-level exams is 3 factors on the denominator. But if you wanted to, you could break this into partial fractions. So it's going to be a constant number over your linear factor there. It's going to be another constant number called a capital B over this linear factor, and then another constant number over the square of this linear factor. But then your last factor, this quadratic one, on the bottom there, we'll give up, well, we'll get on the top of that numerator, we'll have a dx plus capital E, so a linear term on our numerator there. So if you wanted to learn that, you could, but you're not going to be assessed on it. It's really going to be rule number 3 here, so this key rule here, and also rule numbers 1 and 2. They're going to be the key rules that you need. It's just a case of learning those and getting practice with breaking down these fractions into partial fractions.